everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 9 Physics Chapter 3 Laws of Motion. We will be discussing the topic gravitation and also solve questions from exercise 3E. Are you ready for the session? Let's begin. So here in this picture, you can see three people are standing on the surface of Earth. So let's call them A, B and C. To A, B and C will appear upside down. Yes. Are they falling? No, right? They are not falling. There is a force that is holding them. So today in this class, we'll be studying about this force. When I drop a ball to the ground, what happens? It falls to the ground. Am I applying any force? I'm just releasing the ball from my hand. Still it falls to the ground. I'm not applying any force. So in the previous chapter, we have studied Newton's laws. Newton's first law, a body will remain in a state of rest or in the uniform motion unless external force is applied. Here I am not applying any force, I am just releasing the ball. Still it falls to the ground. So there is some other force. Yes? Now when I throw the ball up, what happens? Still it falls to the ground, right? So here what is happening? When I throw the ball up, I am applying a force. Its velocity decreases at maximum height, its velocity becomes 0. With 0 velocity, it is able to fall to the ground. It is able to come to the ground. Here what happens? The velocity of the ball is increasing. So which force helps the velocity to increase? We need to study, right? And this force is called the force of gravity. We are all familiar with this force. So we have studied many examples for this. So what is force of gravity? The earth attracts all objects towards its center. This force of attraction is the force of gravity. Force of gravity is attracting all these bodies towards the center. Okay, and they are able to maintain their position because of the force of gravity which is acting towards the center. Okay, why is a ball falling down? A ball falls down because the earth pulls it. There is a force of gravity. The velocity of ball increases from 0 to a value. Why? Because there is force of gravity. This force helps the velocity to increase. So got a brief idea about what force of gravity is? Yes. So here we have examples for gravity. You can see a mango is falling down. Why is it falling down? Is there any force? Yes. Here the only force that is acting is force of gravity. There is nobody to pluck the mango. Okay. Still the mango falls down. Here gravity is acting downwards. Okay, why does the raindrops from a cloud come down? Here again gravity pulls it down. Gravity is acting in the downward direction. We know Sir Isaac Newton had spoke about gravity or had given an explanation about gravity when an apple fell on his head. Okay, you know the story, right? So here the apple is falling down. Why? Because the gravity, Earth's gravity is pulling apple down. Okay, so here in all these cases, the force of gravity is acting towards the center of Earth, that is in the downward direction. Next is universal law of gravitation. We know that between any two bodies, there is the gravitational force of attraction. Here, I am considering two bodies, M1 and M2. M1 and M2, and the separation between them is R. Now consider mass M1 is equal to 1 kilogram and M2 is equal to 1 kilogram. So in this case, the gravitational force of attraction between them at stake is 1 Newton. Okay. Now what I am doing is I am increasing the mass. Let the mass M1 is equal to 2 kilogram and M2 is equal to 2 kilogram. Then what happens is the force, gravitational force of attraction becomes 4 Newton. Okay, here what happens when the mass increases? What is happening? The gravitational force of attraction is increasing, which means the gravitational force of attraction is directly proportional to the mass. When mass increases, gravitational force of attraction also increases. It doesn't depend only on one mass. It depends on both the masses. Okay, it depends on both m1 and m2, which means the gravitational force of attraction depends on the product of masses. Okay, so for the gravitational force of attraction, two bodies is directly proportional to the product of their masses. Product of their masses m1 into m2. Okay, the gravitational force of attraction is directly proportional to m1 into m2. Now, let us say the distance of separation between them is 1 meter. Okay. Now, the distance of separation is reduced. Let's say the distance of separation is reduced by half. It becomes r by 2, which means now r is 0.5 meter. So, let the initial force be 1 Newton. When the distance of separation r is equal to 1 meter, force is 1 Newton. Okay. Now, when the distance of separation is reduced, force becomes 4 Newtons. Okay. Here what has happened? When the distance of separation decreases, the gravitational force of attraction is increasing, which means F is inversely proportional to the distance of separation, not just the distance of separation, but the square of the distance of separation. Okay, so second statement, inversely proportional. The gravitational force of attraction is inversely proportional to the square of the distance between them. Okay, now one more thing, this force acts along the line joining the two particles. So here you have the line that is joining the two particles. Okay, we know there is a gravitational force of attraction between you and me. Between me and this board, there is a gravitational force of attraction. Between any two masses, there is a gravitational force of attraction. Okay, so it depends on two things. One is the product of masses and the second is the distance of separation between them. So from the universal law of gravitation, when you have two bodies m1 and m2, there is a force of attraction between them. The force on m1 due to m2 is F12 and the force on m2 due to m1 is F21. Okay. Now, the separation is R. We have force F is directly proportional to the product of masses and inversely proportional to the square of distance between them according to the universal law of gravitation. So, when you combine this, what do we get? So, let's call this first and this is second. On combining, we get F directly proportional to m1 m2 divided by r square on combining. So, to remove proportionality, what we do? We used to insert a constant. Okay, here we are inserting a constant. F is equal to G m1 m2 divided by r square. This G is a gravitational constant. Okay, so to find the gravitational force of attraction, this is the formula. F is equal to G m1 m2 divided by r square, where G is the gravitational constant. Gravitational constant. Okay, this gravitational constant is independent of any factors. It does not depend on the nature of the material, it does not depend on the temperature, pressure, anything. Okay, so this is a universally accepted value and therefore G is called universal gravitational constant. Universal gravitational constant. Okay, so F12 and F21. When you take in magnitude, the masses are same, m1 and m2, and the distance of separation is also same. So the value will be same, the magnitude of F12 and F21. That is the force of attraction on m1 by m2 and the force of attraction on m2 by m1 will be the same in magnitude. Clear? We should know one thing, force is a vector quantity. What is a vector quantity? We have studied scalar and vector quantity. Quantities which are dependent only on the magnitude or which has only magnitude are called scalar quantity. Example, mass. Okay, and the quantities which has both magnitude and direction are called vector quantities. Example, displacement, velocity, acceleration, all these we have studied. We know force is a vector quantity. Why? Because force is mass into acceleration. Okay. Acceleration is a vector quantity and mass is a scalar quantity. So, scalar into vector, you will be getting a vector. Therefore, force is a vector quantity. Vector quantities will be representing with an arrow mark above it. Okay. Now, here this means force is a vector quantity. Therefore, it has both magnitude and direction. Here you can see F12 is acting in this direction, that is towards M2. and F21 is acting in this direction, which is towards M1. Okay, it means that we have the value F is equal to G M1 M2 divided by R square. The magnitude will be the same because here the mass M1 and M2 will be same and R, the distance of separation, will also be same. But here what happens is the directions are different. They are in opposite direction, which means we'll be having F12 is equal to minus F21. Okay, which means they are action and reaction forces. Action and reaction forces. So we have studied about action and reaction forces in Newton's third law of motion. For every action, there is an equal and opposite reaction. They act on two different bodies and hence they do not cancel out. Here we have two bodies, M1 and M2. Okay, action force F12 is acting on M2 and F21 is acting on M1. Therefore, they are acting on two different bodies and they never gets cancelled out. Clear? Unit of universal gravitational constant. What are the quantities on which universal gravitational constant depends? We have gravitational force F is equal to G M1 M2 divided by R square, from which we can write G is equal to F R square divided by M1 M2. Okay, what is the unit of force? Unit of force is Newton. Unit of distance or unit of length is meter. We are taking the SI unit. Then unit of mass. Unit of mass is kilogram. So putting the units, we get G. Unit of G will be Newton meter square by kilogram into kilogram, which is equal to Newton meter square per kilogram square or Newton meter square kilogram raised to minus 2. So the unit of gravitational constant is Newton meter square kilogram raised to minus 2. Okay. So this is how you will be finding the unit of a quantity. Unit of, here we are finding the unit of gravitational constant. Newton meter square kilogram raised to minus 2. So how we are getting Newton meter square kilogram raised to minus 2? Understood this? Value of universal gravitational constant. So universal gravitational constant, it does not depend on mass or the distance of separation or temperature or any quantities. It is a fixed value and the value is G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Now consider mass M1 is equal to 1 kilogram, mass M2 is also equal to 1 kilogram and the distance of separation between them R is equal to 1 meter. So we have gravitational force F is equal to G M1 M2 divided by R square. Now put the values. F is equal to G, that is 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Then you have mass M1 1 kilogram, mass M2 1 kilogram divided by distance of separation 1 meter. So 1 meter whole square. Okay, then you will be getting 6.67 into 10 raised to minus 11. So here meter square, this meter square can be cancelled. Kilogram square is in the denominator, kilogram, kilogram. You will be again getting kilogram square in the numerator. That can also be cancelled. Then you will be having Newton. So force F is equal to 6.67 into 10 raised to minus 11 Newton. Which means the universal gravitational constant is equal to the gravitational force of attraction. That is, the gravitational force of attraction between two bodies of masses M1 is equal to 1 kilogram and mass M2 is equal to 1 kilogram and the distance of separation between them is 1 meter will be equal to the universal gravitational constant, or gravitational constant G is numerically equal to the magnitude of force of attraction between two masses of 1 kilogram placed at a separation of 1 meter. Okay, let us take an example. What is the gravitational force of attraction between two bodies of masses? M1 is equal to 1 kg and M2 is also equal to 1 kg at a separation of r is equal to 1 meter. So, how to find gravitational force? Given mass M1 is equal to 1 kilogram, mass M2 is equal to 1 kilogram, and the distance of separation r is equal to 1 meter. So here we have 1 kg mass, which is M1. Here we have 1 kg mass M2, and the separation between them r is 1 meter. We have to find the gravitational force. Gravitational force F is equal to, we have to find. We have gravitational constant G. What is the value of G? Gravitational constant G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Okay. Now, how to find the gravitational force? F is equal to, what is the formula? G M1 M2 divided by r square. We know gravitational force is directly proportional to the product of masses and inversely proportional to the square of the distance between the two masses. Okay. Then what is the force? Put the values. F is equal to G 6.67 into 10 raised to minus 11 into M1 is 1, M2 is also 1 divided by r square, 1 square. So you will be getting 6.67 into 10 raised to minus 11. What is the unit? Unit of force is Newton. Okay. So the gravitational force between masses which are separated by 1 meter and they are of 1 kg is 6.67 into 10 raised to minus 11 newtons. Clear? Second example, what is the gravitational attraction between the moon of mass 7.36 into 10 raised to 22 kilogram and the earth 5.96 into 10 raised to 24 kilogram. Distance of moon from earth is 3.80 into 10 raised to 8 meters. Okay. Here we are given mass of moon is equal to 7.36 into 10 raised to 22 kilogram. Mass of earth is equal to 5.96 into 10 raised to 24 kilogram. Okay. Then separation between them. Separation r is equal to 3.80 into 10 raised to 8 meter. So here we will take this as M1 and this as M2. Mass of moon we are taking as M1 and mass of earth as M2. Now what is the gravitational force? F is equal to G M1 M2 divided by r square. Gravitational constant G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Okay. Now put the values to find gravitational force. F is equal to 6.67 into 10 raised to minus 11 into M1 is 7.36 into 10 raised to 22 into 5.96 into 10 raised to 24 divided by r square, that is 3.80 into 10 raised to 8 whole square. Okay. So when you calculate this, use your calculators and find, you will be getting the value 2 into 10 raised to 20 newtons. Okay. So here we can see the bodies are moon and earth. In the previous question, we have seen that mass M1 is 1 kg and M2 is 1 kg. So compared to this, they are very small bodies, right? They are not that massive. Here we have heavenly bodies which are massive. And in that case, gravitational force is also higher. Yes. In the previous case, we got gravitational force is equal to 6.67 into 10 raised to minus 11 newtons, which is a very small force compared to this. This is 2 into 10 raised to 20 newton. Okay. Understood? Gravitational force of attraction is highly significant between heavenly bodies, but it is insignificant between ordinary bodies. So in the first example, when we had taken 1 kilogram masses, okay, 2 masses of 1 kilogram when considered, we had got force F is equal to 6.67 into 10 raised to minus 11 Newton. Okay, here you can see the power is 10 raised to minus 11 Newton, which means it is a very small value. So when we took the second example, that is the gravitational force of attraction between Earth and Moon, we got a value which had a power 10 raised to 20 Newton. 10 raised to 20 Newton means it is very significant, it is a very high value. Okay, so this is very important. So between every bodies there is force of attraction, but the only thing is between ordinary bodies it is not that significant. Why? Because the masses are very small. So when you take heavenly bodies, they are heavy masses or they are massive bodies, and because of this reason the gravitational force of attraction will also be very significant. Properties of gravitational force. Gravitational force between two bodies is, first point, always attractive. So we have F is directly proportional to m1 m2 divided by r square, or F is equal to g m1 m2 divided by r square. Okay, this gravitational force, you can see it is acting between two bodies, between two masses, and this force is always attractive. Between m1 and m2 there is an attractive force. Okay, second point is directly proportional to the product of masses. Yes, F proportional to m1 into m2, from which we have the universal law of gravitation. Okay. Third point, inversely proportional to the square of separation between them. F is inversely proportional to 1 by r square, or F proportional to 1 by r square, which means when the distance of separation decreases, the gravitational force increases. Okay. Now the fourth point, significant between heavenly bodies but is insignificant between ordinary bodies because of small magnitude of g. Clear? So these are the important points. Force of gravity obeys inverse square law. We have force of gravity, or the gravitational force of attraction, F directly proportional to mass m1 into mass m2 divided by r square. Force is inversely proportional to the square of the distance of separation between them. Now, let's say two masses m1 and m2 are at a separation of r. Then what is the force? F will be equal to g m1 m2 divided by r square. Now the distance of separation is reduced to half, that is m1 m2, and the distance of separation now is r by 2. Okay, distance of separation becomes half. Then what happens to force? New force F dash will be equal to g m1 m2 divided by r by 2 whole square equal to g m1 m2 divided by r square by 4 equal to 4g m1 m2 divided by r square. We have g m1 m2 divided by r square equal to force F, that is 4 into F, which means the new force when the distance of separation is halved will be equal to 4 times the actual force when the distance of separation is r. Okay. Now, if the distance of separation is doubled, m1, m2, okay, r becomes 2r. Then what happens? We will be having the new force F double dash equal to g m1 m2 divided by, here it will become 2r whole square, that is g m1 m2 divided by 4r square equal to 1 by 4 into g m1 m2 divided by r square. G m1 m2 divided by r square is the actual force. So this is F divided by force. Okay, which means when the distance of separation is doubled, force becomes 1 by 4. Okay, so when distance of separation is halved, force becomes doubled. Okay, and when the distance of separation is doubled, then force becomes 1/4. Okay, clear? Importance of universal law of gravitation. Newton used the universal law of gravitation mainly to explain three things. First is the motion of planets around the sun. We know planets are revolving around the sun in circular orbit. There is a force of attraction, which is the gravitational attraction between the sun and the planets, that helps them hold to orbit around the sun. Okay. Second is the motion of the moon around this earth. So you can see earth is at the center and the moon is revolving around the earth. So here they are able to maintain their position because of the gravitational force of attraction between them. Next is the motion of freely falling body. Any body that is falling to ground. Why is it happening? Because there is a gravitational force of attraction or the force of gravity which pulls every body down. Okay, force due to gravity. According to the law of gravitation, the earth attracts every object around it towards its center. The force with which the earth attracts a body is called the force of gravity or force due to gravity, and it is acting vertically downwards. We know all this, right? So we have force F is equal to G m1 m2 divided by r square. Now consider a body of mass m which is on earth. Okay, let mass of earth be taken as capital M, and we know the mass of earth, the value is 5.96 into 10 raised to 24 kilogram. Okay, and let the mass of body be M is equal to 1 kilogram. Then radius of earth, capital R is equal to 6.37 into 10 raised to 6 meter. Okay, now we can find the force. We have force F will be equal to G. The first body M1 is of mass capital M, which is the mass of earth. Okay, and M2 is the mass of the body small m, R square. Okay, which is equal to 6.67 into 10 raised to minus 11 into mass of earth is 5.96 into 10 raised to 24. Let the mass of body be 1 kg divided by 6.37 into 10 raised to 6 whole square, radius of earth square. Okay, then F, we will be getting the value 9.8 Newton. So we can conclude that for a body of mass 1 kg on the surface of earth will be having a force due to gravity equal to 9.8 Newton. Now the earth attracts a body. Okay, so this is an action force. Similarly, the body will attract the earth, but you can see that the body is free to move. What about earth? Earth is a massive object, it's not free to move. So you can see the body will be moving, but earth does not move. Still there is the force of attraction between the body and earth. Okay, with how much force the earth attracts a body, same in magnitude will be the force with which the body attracts the earth. Clear? Galileo was the first scientist who studied the motion of different objects under the force of gravity. So he performed an experiment. He used a bowl and a feather and they were made to fall. Okay, this is happening in vacuum. So in vacuum there is no medium. In that case the bowl and feather will be falling at the same rate. That is, the speed will be the same. Okay, and the time taken for the travel will also be the same. Okay, now if you drop a bowl and a feather, okay, you are taking a feather and a bowl and you are dropping. What happens? You can see that the bowl will fall down easily. Okay, it will take less time, but the feather will be taking more time. But this is not the case in vacuum. In vacuum, where there is no medium, bowl and the feather will be falling at the same time. Okay, so this was a conclusion made by scientist Galileo. If bodies of different masses, you can see the feather is of less mass. Mass of feather is less than the mass of bowl. And sizes are simultaneously made to fall in vacuum from the same height, they all reach the Earth's surface simultaneously and with the same velocity. The time taken will be same and the velocity will also be the same. Okay, this will happen only in vacuum. Remember that point. Acceleration due to gravity. When a body is falling freely, we know that its velocity does not remain a constant, it is continuously increasing. So, it is increasing uniformly. Therefore, this is an example of uniformly accelerated motion. And the acceleration involved here is acceleration due to gravity. Okay, acceleration due to gravity we represent by letter G. Okay, and its value is 9.8 meter per second square. It is an acceleration, therefore the unit will be meter per second square. Okay, this acceleration due to gravity we can define as the rate at which the velocity of a freely falling body increases is called the acceleration due to gravity. It is the acceleration produced in a freely falling body due to the gravitational force of attraction of the earth. Here we know velocity increases or the acceleration change is happening only because of a force, and this force is a force of gravity. The value of G is independent of mass, size and shape of the body. Okay, the same for every object. It is independent of the mass. Now, the value of G is not same on every surface of the earth. Okay, at different points it will be different. For example, the acceleration due to gravity at the equators will be slightly less than that at the poles. Okay, and the acceleration due to gravity is 0 at the center of earth. Center of earth, acceleration due to gravity is 0 and it is maximum at the poles. Okay, now the value of acceleration due to gravity decreases when the height from the Earth's surface or the depth from the Earth's surface increases. Okay, dependingly the acceleration due to gravity is decreasing. Now, what is the unit of acceleration due to gravity? We said the unit of acceleration due to gravity is meter per second square. Is it a scalar quantity or vector quantity? Acceleration due to gravity is acceleration. Acceleration we know is a vector quantity. Therefore, acceleration due to gravity is also a vector quantity. Okay. As we said, this is the value of acceleration due to gravity on the surface of Earth. It is not the same in Moon or any other planets. It will be different. Clear? Now, what is the relationship between acceleration due to gravity and gravitational constant? We have studied Newton's second law of motion. So, according to Newton's second law of motion, we have derived the equation of force. Okay. We have got an equation for force. What was it? F is equal to ma. So, here the acceleration is acceleration due to gravity. So, F is equal to mg. Take this as the first equation. Okay. Then now we have studied universal law of gravitation, according to which force F is equal to G m by r square. Okay. Capital M is mass of Earth, small m is mass of body and r is the radius of Earth. G is the universal gravitational constant. Okay, you can see when you compare these equations, left hand side is the same. So, right hand side also should be the same. Okay, therefore, m into g is equal to g capital M small m divided by r square. Small m can be cancelled, then g is equal to capital G m divided by r square. So, to get the value 9.8 meter per second, you just need to substitute here. Okay, g 6.67 into 10 raised to minus 11. Then mass of Earth and the radius of Earth when substituted. Doing the calculation, you will be getting g value is equal to 9.8 meter per second square. So, if these values are given, you can find the acceleration due to gravity. Okay, so this is a relation between universal gravitational constant and the acceleration due to gravity. Okay, value of G on a planet or satellite depends on the mass and radius of that planet or satellite. Okay, it does not depend upon the mass of the body. G, we can see G is independent of the mass of the body. It depends only on the mass of the planet or the satellite and the radius. Okay, if it is moon, you will have to substitute the values here for the mass of moon and the radius of moon. Then you will be getting the acceleration due to gravity on moon. Clear how to calculate G? We'll take an example. What is the acceleration due to gravity at a place on the surface of Earth of mass 5.96 into 10 raised to 24 kilogram, and the radius of earth r is equal to 6.37 into 10 raised to 6 meters. We have to find the acceleration due to gravity. Given mass of earth m is equal to 5.96 into 10 raised to 24 kilogram. Next, the radius of earth. Radius of earth r is equal to 6.37 into 10 raised to 6 meters. Now, how to find acceleration due to gravity? Acceleration due to gravity on earth, g earth is equal to gravitational constant g, mass of earth m, radius of earth square r square. Okay, that is equal to. So first we need the value of g. What is the value of g? 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Okay, now g, small g is equal to, we have the relation between acceleration due to gravity and gravitational constant. Small g is equal to capital G m divided by r square. Okay, from which we can put the values. G is equal to 6.67 into 10 raised to minus 11 into, what is the mass of earth? 5.96 into 10 raised to 24 divided by r square, that is 6.37 into 10 raised to 6 whole square. Okay, so when you calculate this, approximately you will be getting the value 9.8 meter per second square. So remember, here the unit is meter per second square because acceleration due to gravity is an acceleration due to the earth. Okay, clear? So 9.8 meter per second square is acceleration due to gravity on earth. Example 4. What is the acceleration due to gravity at a place on the surface of moon of mass 7.36 into 10 raised to 22 kilogram, and the radius of r is equal to 1.75 into 10 raised to 6 meter? What is the relation between acceleration due to gravity on earth and the acceleration due to gravity on moon? Okay, first we will find the acceleration due to gravity on moon. We are given mass of moon m is equal to 7.36 into 10 raised to 22 kilogram. Then we have radius of moon r is equal to 1.75 into 10 raised to 6 meter. Gravitational constant g will be the same, which is 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Therefore, acceleration due to gravity on moon is equal to gm divided by r square, that is 6.67 into 10 raised to minus 11 into 7.36 into 10 raised to 22 divided by 1.75 into 10 raised to 6 whole square. So when you calculate this, approximately you will be getting a value 1.6 meter per second square. So acceleration due to gravity on moon is 1.6 meter per second square. Now we need to find the relation between acceleration due to gravity on moon and acceleration due to gravity on earth. Okay, we have acceleration due to gravity on earth, which we had determined in the previous example, equal to 9.8 meter per second square, and acceleration due to gravity on moon, now we have determined, which is 1.6 meter per second square. Now taking the ratio, acceleration due to gravity on moon divided by acceleration due to gravity on earth is equal to 1.6 divided by 9.8. Okay, so when you take this ratio, approximately you will be getting 1 by 6. So g moon by g earth is approximately 1 by 6, which means the acceleration due to gravity on moon will be approximately 1 by 6 the acceleration due to gravity on earth. So remember this relation, acceleration due to gravity on moon is approximately equal to 1 by 6 the acceleration due to gravity on earth. So here the approximation comes because in case of this finding the G moon and G earth, we are not getting the exact value. We are rounding it to 1.6 and 9.8. Okay, so when you take the ratio, you will be getting 1 by 6. Fifth example, calculate the gravitational force of attraction between two bodies of masses 40 kg and 80 kg separated by a distance of 15 meter. There is a 40 kg mass, then you have a 80 kg mass. They are separated by 15 meter distance. Okay, so M1 is equal to 40 kilogram, M2 is equal to 80 kilogram, distance of separation R is equal to 15 meter. Gravitational force F we have to determine, which is G M1 M2 divided by R square. So F is equal to 6.67 into 10 raised to minus 11 into 40 into 80 divided by 15 square. Okay. So when you calculate this, you will be getting the value 9.5 into 10 raised to minus 10 Newton. Gravitational force, the unit is Newton. Any force, the unit is Newton. So this is the value of gravitational force between masses 40 kilogram and 80 kilogram separated by 15 meters. Let us take a question from exercise 3E, question 1 of exercise 3E. The force of attraction between two bodies at a certain separation is 10 Newton. What will be the force of attraction between them if the separation is reduced to half? Okay, here we have two bodies, M1 and M2. Separation between them is R. Okay, then what will be the gravitational force? F is equal to G M1 M2 divided by R square. This is the gravitational force. Yes. What is it given? The force of attraction between two bodies at a certain separation is 10 Newton. This force is equal to 10 Newton. So, we will call this force as F1. F1 is equal to G M1 M2 divided by R square, and that is equal to 10 Newton. Now, what is given? What will be the force of attraction between them if the separation is reduced to half? That is, here we have M1 and here we have M2. The distance of separation between them becomes half, which means R divided by 2. Okay. So, force F2 will be equal to, masses will be same because the value of mass is a constant that cannot change. M1 M2 divided by R by 2 whole square. We have to find this. Okay. So, we are taking the ratio F1 by F2. We have F1 is G M1 M2 divided by R square divided by G M1 M2 divided by R by 2 whole square. That is equal to 10 Newton divided by this force we don't know. Okay, so let us take it as F2 itself. Okay, then what is F2? How to find F2? F2 will be equal to, okay, we are cross multiplying. This is the numerator, this is the denominator. F2 will be equal to, already we have 10 Newton here. Okay, this goes to the numerator. Okay, that is G M1 M2 divided by. Now this R by 2 whole square. What is R by 2 whole square? R square divided by 4. Okay, R by 2 whole square is R square divided by 4. So taking the reciprocal, that is, you can take the denominator to this numerator. So 4 comes here, then you will be having R square in the denominator. Okay, now here this term when goes down, it becomes G M1 M2 divided by R square. Okay, so cancelling R square, G M1 M1 M2 M2. Then you will be having F2 is equal to 10 Newton into 4, or F2 is equal to 40 Newtons. Okay, so the gravitational force of attraction between M1 and M2 when the distance of separation is halved is 40 Newton. So we have the relation force is inversely proportional to the square of the distance of separation between them. Yes. So here when R reduces, what happened? That is, the distance of separation reduces, gravitational force will increase. Okay. Same thing has happened. We have reduced the distance of separation by half, and then what happens? The gravitational force becomes 4 times. Okay. Gravitational force becomes 4 times. Clear? That's all for today. In today's class, we have discussed the topic gravitation. We have discussed the universal law of gravitation, and we have studied about the acceleration due to gravity. So we have discussed many examples. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to Learno Hub. Learno Hub free hai, par best hai. Thank you.